Good day. Solving day 2. So in solving day 2, I want to take a look at lots of different situations. And this material will, it's directly related to assignments number 1 and 22. I'm toying whether I should make one long video that covers all the methods, or if I should split it into two. I'm probably going to split it into two, but really it could be done as one session, all about solving lots of different things. So let's start with, of course, some bell work, where we solve this equation. Okay, we solve that equation. Welcome back. That's x plus 4, x plus 2. So x plus 4 equals 0 and x plus 2 equals 0. And you get x equals negative 4 and x equals negative 2. And that's great. But, oh, by the way, I meant to say solve this by completing the square. So will you please solve this by completing the square? All right. So how do we do that? It was just in the last video. Remember, isolate x stuff was first. Then get our a value equal to 1 by dividing by a everywhere. Then step 3 was to add b over 2 squared to both sides. Then we wrote the perfect square trinomial. And finally took the square root of both sides. All right, well, in that time, I hope most of you were able to actually do completing the square here. So remember, we want to isolate the x stuff, so I'm going to subtract 8 from both sides. X squared plus 6x equals negative 8. Oops, negative 8. And now I'm supposed to get a equal to 1 by dividing by a. My a is equal to 1, so I can skip that step. Now let's add b over 2 squared to both sides. My b value is 6. 6 divided by 2 is 3. I'm adding 3 squared and 9 to both sides. Remember, I don't actually do the squaring over here because that facilitates my writing the perfect square trinomial in factored form. This 3 comes to both of these places. And then I've got x plus 3 squared equals 1. You take the square root of both sides. X plus 3 equals what? No, not 1. What? We took the square root of both sides. Plus and minus 1. X equals negative 3 plus and minus 1, which means x equals negative 2 and x equals negative 4. And yes, I still agree, completing the square, it's a lot of work. I'd much rather do factoring, I'd much rather do quadratic formula, but that doesn't mean we don't get the opportunity to practice this. So, would you be so kind as to use completing the square on 8x squared plus 16x equals 42 and solve that one? Okay, welcome back. So, I've got my x stuff isolated, but I don't have a equal to 1. So I need to divide everywhere by 8. So I'm going to have x squared plus 2x equals, take a 2 out of both of those. All right, now what? Well, now we're supposed to add b over 2. My b value is 2. 2 divided by 2 is 1. To both sides. On the left-hand side, I now have a perfect square trinomial. On the right-hand side, when I add these, this is 4 over 4 plus 21 over 4, I have 25 over 4. This is the perfect square trinomial x plus 1 squared 25/4. Now we can take the square root of both sides. Get x plus 1 equals what? Say it loud. That's right, plus and minus 5/2, which is going to give me x equals -1 plus or minus 5/2. Yes, I do expect you to take that a little further. X equals -1 plus 5/2. It's 2.5 minus 1, which is 1.5 or 3/2. And -1 minus 5/2 is going to be -7/2. I need to see both answers. Okay? You know, completing the square wasn't that bad there. In fact, when I think about the original problem, 8x squared plus 16x equals 42. You know, would I really want to use quadratic formula on this or completing the square? Not really. B squared equals 256. That's a big number. And what about trying to factor this trinomial? Ah, that's going to be such a bear to try and figure out. Is this 8 and 1 or 4 or 2? 6 or 7? And just, yeah, so sometimes maybe completing the square can be okay. All right, so let's take a look at some of our new problems. Today, we're going to run into must checks number 2 and number 3. Remember, must check number 1 is x stuff in the denominator. Okay, that's number 1. We will be seeing 2 and 3 soon now. Let's start doing some problems, though. I guess I want to, these next problems, these first problems, the first section. The first section is going to be solving polynomials, which could include quadratics. And generally what we're doing with polynomials, not always, but generally, is we're factoring, okay? But not always. So when I think about solving polynomials, we start gently. How about 3x to the 4th minus 48 equals 0? All right, so here, I remember if I'm thinking about, wow, I could do this a bunch of different ways, couldn't I? I really can. So let's say first way by factoring. So I'm going to factor out a 3 from both sides, from both of these terms, x to the 4th minus 16, a difference of squares. So that's going to be x squared minus 4, x squared plus 4. Oh, another difference of squares. It's minus 2, x plus 2. And this is a sum of squares. This will only produce imaginary roots. So I don't have to go any further with that. So what are my solutions? X equals 2 or negative 2. And that was by factoring, setting each factor equal to 0. Remember, when I set x squared plus 4 equal to 0, I get x squared equals negative 4. I can't take the square root of negative 4 and get a real number, so I don't bother with that, just these two. All right, so there's this other approach, though, and that is that I could take the root. Wouldn't be square root this time, but to do that, I want to isolate the x. Now I'll divide both sides by 3, and now I'll take the 4th root of both sides. So the 4th root of both sides is 2 times 2 times 2 times 2. I need a group of 4 to get out from under. Well, I have 4 2's. And remember, you took the 4th root of both sides. It's an even index root, which means don't forget the plus or minus. So we end up with plus and minus 2 here. So we could do this either by taking the root and isolating that x to the 4th and taking the 4th root of both sides, or we could do this by factoring. Either one, perfectly fine. I mean, I guess you could even do quadratic formula, 3x x to the fourth minus 48 equals 0. Our a equals 3, our b equals 0, our c equals negative 48. And remember how the quadratic formula looks like x equals negative b? Well, here it's not x equals negative b. It's x squared equals negative b plus or minus square root of b squared minus 4ac all over 2a. Yeah, ew. So while I could do this with quadratic formula, look, it's only going to tell me what x squared is. I still need to take the square root of both sides when I'm done. I don't want to do that. So let's move on to our next problem instead. How about this one? X to the third plus 2x squared plus 3x plus 6 equals 0. What can you do here? Well, that's right. If I'm using factoring, I've got 4 terms, then I can do factoring by grouping. Okay, so I can pull out an x squared here, and I can pull out a positive 3 here, and then I can say, oh look, they both have an x plus 2 in common, factor that out, leaving me with x squared plus 3. So now that I have these factors equal to 0, I'm supposed to set each factor equal to 0. Now this is going to make x equals negative 2. But what about this one? I'm going to subtract 3 from both sides and take the square root. Can I take the square root of a negative number? No. So that doesn't produce any solutions. I only get one solution there. All right? How about this one? How about x to the fourth plus 5x squared minus 36 equals 0? Well, it's a quadratic trinomial? No, it's a quartic trinomial. But this is going to factor the same way this did. Remember factoring this, and we said x plus 9, x minus 4 equals 0? Except with this one, it's going to be x squared plus 9 and x squared minus 4 equals 0. When I set each of these factors equal to 0, I see that this doesn't produce any real solutions, and that makes sense to me because I'm talking about a parabola shifted up 9 places and asking the question, when does that parabola intersect the y-axis? It never intersects. But this parabola shifted down 4 places, yeah, it intersects in two places. So x squared equals 4, x equals, don't forget the plus or minus, x equals plus or minus 2. Okay, so we get 2 imaginary solutions, 2 real solutions, and in our algebra basics unit, I only need the real solutions, okay? So how about this one? How about x to the 6th? Oh, no, I don't want to do that one. I want to do this one. Yeah, I do want x to the 6th plus 3x to the 3rd plus 2 equals 0. Will you pause the video and try solving this one? Okay, so this factors as x to the 3rd plus 2 and x to the 3rd plus 1 equals 0. So I get x to the 3rd plus 2 equals 0, and x to the 3rd plus 1 equals 0. So I get x to the 3rd equals negative 2, or x equals cube root of negative 2. X to the 3rd equals negative 1, or x equals cube root of negative 1, which turns out to be negative 1. Mr. Koopa, why are you taking the root of a negative number? Well, think about this graphically. It's our x to the 3rd graph shifted up 1. Does this x to the 3rd graph shifted up 1 ever equal 0? Sure does. And what about an x to the 3rd graph shifted up 2? Okay, now it's shifted up 2. Doesn't that equal 0 somewhere? Sure, at cube root of negative 2. Remember, I can take the cube root of a negative number, I can't take the square root of a negative number. So when I see the factors x squared plus 1 and x squared plus 2, then I say no real solution, because these parabolas never intersect the x-axis. But these x to the third functions, they definitely get the x-axis. Okay, how about this one? It's not a polynomial, but it follows a similar pattern. X plus 5 root x minus 36 equals 0. Aha! This is the same as x squared plus 5x minus 36. And remember this one that we did a few minutes ago? We were able to factor this one. This is following that same pattern. Well, let's go. This is root x plus 9, root x minus 4. So I'm following that same pattern that I would have gotten for x squared plus 5x minus 36, which was x plus 9, x minus 4. But instead of x's here, because this is an x, I'm using square root of x because that's square root of x. I'm still going to set each factor equal to 0. I get square root of x equals 4. I square both sides, which gives me x equals 16. I'm going to subtract 9 from both sides. Root x equals negative 9. Then I'm going to square both sides and get x equals 81. All right, nice. Oh, by the way, this is our second must check. This is must check number 2. Must check number 2 is when you square both sides of the equation. If you square both sides of the equation like we did here, yeah, these are now must-check answers. Let's go back to our original problem, x plus 5 root x minus 36 equals 0. And let's plug these in. Okay, square root of 81 is 9. 9 times 5 is 45. So I have 81 plus 45 minus 36 equals 0. Is that true? 126 minus 36 is 0? No, that's not true. That's garbage. How about this one over here? Let's plug in 16. Square root of 16 is 4. 4 times 5 is 20. And then here I have 16. Oh, 36 minus 36 does equal 0. Yeah, that's my answer. So look, you have to check a must check. If you go through and solve this problem and get these two numbers and say these are my answers, it gets marked wrong and you've lost all those points. But if you remember what your must checks are, and they're not ought checks. I'm not saying I ought to check this, it's must check. If I do this thing called squaring both sides of the equation, that requires me to now plug my answers back in and see if they work. 81 did not, 16 did, I get one solution here, okay? If you don't check your must checks, you will probably get all of those problems wrong, where you're supposed to be must checking, okay? So please be careful with that. All right, next. Let's take that idea of working with radicals a step further, and that's what we're going to do, be solving equations with radicals. So, how about this one? 4 root x minus 3 equals 0. Ah, very nice. Very Algebra 1 level difficulty. Why don't you try solving this one and see what you get. Pause the video, come back when you're done or have questions. Okay, so I need to isolate the radical. Before I square both sides. So I'm going to add 3, and then I'm going to divide by 4. So I get square root of x equals 3/4. And now I'm not going to take the square root of both sides. I'm going to square both sides. X equals 9 over 16. Right here, where I squared both sides, remember that's must check number 2. So I'm going to take this 9/16 and plug it in here. Plug it into the original equation. Square root of 9 is 3, square root of 16 is 4, so I've got 4 times 3/4 minus 3 equals 0. Oh, the 4's cancel, leaving me 3 minus 3, which really is equal to 0. So this one works fine. But remember, if I square both sides, that's a must-check situation, so please make sure you must check it. Okay, how about this one? Square root of 5 minus x minus 3 equals 0. Again, when I've got a radical, I don't want to square both sides until I've isolated the radical. Otherwise, my squaring would have to look like this, and that'd be foiling, and it's not going to get rid of the radical. It's just going to make things worse. So let's isolate that radical before we square both sides. So we get 5 minus x equals 9. I'm going to subtract 5 from both sides. I get x equals negative 4. Okay, does this work? Is this a must check? Well, I squared both sides, so I have to plug this in. Now, there are some students who say, but Mr. Kukla, you can't have a negative with that radical. And I would agree I can't take the square root of a negative, but am I really? Because I have a minus 4 going in here. So it's going to be 5 minus a minus 4. Well, that's 5 plus 4, or 9. So square root of 9 is 3, 3 minus 3 is 0, and that works perfectly. So how about this one? Cube root of 3x plus 1 equals 5. What do I need to do to get rid of this cube root? That's right, I need to cube both sides. So I get 3x plus 1 equals 125, or 3x equals 124, or x equals 41 and 1/3. I guess you could certainly write it as 124 over 3 just as well, and that would be fine. And remember, this is cubing both sides. That's not an even power, so this isn't a must check. There's no restriction on my domain for cube root of x. Remember our reference graph. You can plug in any x you want and get a y value. So I'm not worried about this one. It's if I square both sides, or I raise both sides to the 4th power, which I almost never do. That's when I have a must check. Okay? So how about this one? Square root of x plus 5 equals square root of 5 minus x. Well, this is convenient. I've just got one radical here and one radical here, so why don't we square both sides? X plus 5 equals 5 minus x. Add x to both sides. I subtract 5. I get x equals 0. So does x equals 0 work? If I plug a 0 in there, and I plug a 0 in there, then I have square root of 5 equals square root of 5. That's great. No problems. All right. What about this one then? What about square root of x minus 1 equals x minus 7? So the radical is isolated, which means I need to square both sides. And here, I'm going to get x minus 1. But here, I've got a FOIL, right? Because that's x minus 7 times x minus 7. So x minus 1 equals x squared minus 14x plus 49. And because this is bigger than first degree, I'm going to move everything onto one side. I get x squared minus 15x plus 50. This factors as x minus 10, x minus 5, and so I end up with x equals 5 and x equals 10. Am I done? No, I'm not done, because the very first thing I did was to square both sides of the equation. All right, so let's plug in 5. 5 minus 1 is 4. Square root of 4 is 2. 5. 5 minus 7 is negative 2. Those are not the same. This is garbage. Let's plug in 10. 10 minus 1 is 9. The square root of 9 is 3. 10 minus 7 is 3. 3 does equal 3. So I do get one solution here. All right? You have to check these. I'm never gonna know when I have an extraneous solution. I just know that when I square both sides of an equation, I might be introducing an extraneous solution into my work. All right, so how about this one? 5 minus x under the radical minus 1 equals x. Please try that one. Okay, welcome back. I hope you remembered to isolate the radical first before you squared both sides. And when I square both sides, I have some FOILing to do over here. So this is 5 minus x equals x squared plus 2x plus 1. Because this is second degree, I want to move everything onto one side. So I'll add x to both sides and subtract 5 from both sides. This is going to factor as x plus 4, x minus 1. And when I set each factor to 0, I get x equals negative 4 and x equals positive 1. All right, do both of those solutions work? Well, in order to find out, we need to go back to our original equation. Let's plug in a 1. 5 minus 1 is 4, square root of 4 is 2, 2 minus 1 is 1, and I'm plugging in a 1. So this works. Nice. What if I plug in a negative 4? Okay. Minus a minus 4. 5 minus a minus 4 is 9. Square root of 9 is 3. 3 minus 1 equals negative 4. No, 2 doesn't equal negative 4. So that's garbage, and I get only one solution. Okay? I mean, you can think about these problems graphically, by the way. So, we did transformations with this. We know that this goes like that, and we know that this goes like that, and I see a point of intersection over here in negative land. It turned out it was negative 4. No, negative 4 didn't work. It was positive 1. Ooh, I must have drawn this wrong. Negative x plus 5. Oh, I shift it left, and then I reflect it, and I shift it down. Huh. That's surprising. Oh, not upside down. That's silly me. This way. Down 1, like that. There we go. One solution. Okay, so think about it graphically. That might help you figure out whether you have some extraneous solutions or not. So that was dealing with radicals. Now, our third type, solving equations with rational exponent powers. So, we could look at square root of x equals 3 as x to the 1/2 equals 3. And what do I have to raise each side to clear this out? Well, because when I raise a power to a power I'm multiplying, I want to multiply by the reciprocal. So over here, I raise 3 to the power of 2. Okay, and that's going to give me x, and over here, I'm going to get 9. All right? So we could think that instead of using radical symbols, we could use rational exponents, like this one. X plus 3 to the 3/2 equals 8. Now, I don't want to write this as a radical, right? It's going to be the square root of x plus 3 to the 3rd. Ew! I don't. I really just want to use this rational exponent. Okay, so what do I need to raise both sides to? To 2/3. Raise both sides to the reciprocal power. Okay? Because when I raise a power to a power, I'm multiplying. And when I multiply reciprocals together, I get 1. X plus 3 to the 1 is just x plus 3. Now over here, what did we say at the beginning of this algebra basics unit we would do here? Rewrite the base. That's 2 to the third to the 2/3. And when I raise a power to a power, I multiply, so those cancel. And I get 2 squared, or 4. So x plus 3 equals 4. I subtract 3 from both sides, I get x equals 1. Okay, if I plug this 1 back in, 1 plus 3 is 4. The square root of 4 is 2. 2 cubed is 8. Ta-da! There's my answer, x equals 1. Okay, so let's try some more of these. How about x plus 2 to the 2/3 power equals 9? Why don't you try this one? Pause the video, give it a try, come back when you're stuck or you're done. Welcome back. So did you raise both sides to the 3/2 power? And did that give you x plus 2 equals, so 9 to the square root of 9 is 3, and 3 to the third is 27. And so x would equal 25. Is that it? Is that our only answer? Well, I've been saying, let's take a look at these problems graphically. And I think I'd like to do that again now. Let's graph this equation in y1 and this in y2 and see how many points they intersect. We think they intersect at positive 25, so I want to make sure my x's go far enough to the right to see that number. Okay, so let's see what we've got here. Parentheses, x plus 2, close parentheses, raised to the power of 2/3. Okay, and the other line, 9. And I want my y max to go past 9, so I'm going to say, how about 15? And that could be 0. And then what about my x's? Well, 25 is way out there. So I'm going to say negative 50 to positive 50 in steps of 10. Graph. Okay, remember, we're looking for points of intersection. How many do you see? 1, 2. How many did we have? Only 1. How come? Because when you take the square root of both sides, you're supposed to remember the plus and minus. But I didn't take the square root of both sides. See that? That's you taking the square root of both sides. You're raising both sides to the 1/2 power. So, something to watch out for here is whenever you raise to a power whose denominator is even, don't forget the plus minus. Okay, so when we raised this side, both sides, to the 3/2, our denominator was even, and that means our next step should have been plus and minus. Square root of 9 is 3, 3 to the third is 27. And so when I subtract 2, I'm going to have x equals negative 2 plus and minus 27, which is 25, or negative 29. So there are 2 points of intersection, and I'm not going to find them unless I remember that plus or minus. Why? Because this denominator was even. Okay? So whenever we have an even denominator, I've got to remember a plus or minus there. All right, how about this one? X squared minus x minus 21 to the 3/2 equals 27. Okay, so I raise both sides to what power? to the 2/3 power. Is this denominator even? No, it's odd. So why don't you finish the problem? Pause the video, come back when you're done. Hey, welcome back. So I know over here, when I multiply those reciprocals, I end up with x squared minus x minus 21. And over here, I want to rewrite the base. 27 is 3 to the 3rd raised to the 2/3. These 3's cancel, leaving me 3 squared, or 9. Because this is a quadratic, I want to move everything onto one side. X squared minus x minus 30 equals 0. And that's going to factor. And x equals 6, and x equals negative 5. Okay, so is this a must check? Well, did I square both sides? That's squaring both sides. So let's must check this. Let's go back to our original, which doesn't have those. So if I plug in a 6, I get 36 minus 6 minus 21. That's 36 minus 27, which is going to be 9. So on the left-hand side, I have 9 to the 3 halves. 9 to the 3 halves. The square root of 9 is 3. 3 to the 3rd is 27. So that one worked perfect. What about that second solution, negative 5 that we had? Remember, our original equation was x squared minus x minus 21 raised to the 3 halves equals 27. So if I plug a negative 5 in here, I'm going to get 25. Negative 5 times negative is plus 5 minus 21. So 30 minus 21 is 9 to the 3 halves equals 27. And yes, it does. Both of these work. Okay? Both of these work. So let us do one more. I think we need one more. Don't you think we need one more? How about this one? Oh, this one is brilliant. 4x squared, x minus 1 to the 1/3, plus 6x, x minus 1 to the 4/3 equals 0. You know what this is? This is one of those GCF factoring problems. Look, I've got two terms, and now I look for what they have in common. They have a 2 in common. They have an x in common. They have an x minus 1 to the smallest power in common. And so what's left over? Well, I took out a 2, so I still have a 2. I took out an x, so I still have an x. And I took out all of that. So I just have 2x from the first term. Then my plus sign. We took out a 2, so we have a 3 left over. We took out this x, that's gone. And we took x minus 1 to the 4/3 and divided it by x minus 1 to the 1/3. And so when I subtract those powers, I get x minus 1 to the 3/3, which is just x minus 1. Okay? So now we've got 2x, x minus 1 to the 1/3. Here, 2x plus 3x is 5x. Don't forget to distribute that minus 3. All right. So now we've got 3 factors. We set each factor equal to 0. I get x equals 0. I get x equals 1. I get x equals 3/5. Do you think this is a must check, or is it just an ought check? Well, I don't know. I better check. If I plug in a 0, I get 0 plus 0 equals 0. So that one's good. If I plug in a 1, 1 minus 1 is 0. Cube root of 0 is 0. So I get zeros times stuff. It's just going to be 0 plus 0 again. So that works. What about 3/5? 1 minus 3/5. Ooh, that's negative. Is that a problem? Well, that's going to be negative 2/5 to the 1/3 power. And here, if I put in 3/5 and square it, I get 9 over 25 times 4, plus 6 times 3/5. And here we have negative 2/5 to the 4/3 power. Wow. Could those be the same? They don't look the same. I'm not sure. Are they the same? What can I do to figure out if this works or not? Well, I can do a couple of things. I can take the cube root of this and raise this to the 4/3 power. I can do this on my calculator and check. So I've got -2/5 to the 1/3 power. And I want to multiply that by 36 and divide that by 25. And so I get -0.192 for the first term. But what about over here? When I have -2/5 raised to the 4/3 power, and I want to multiply that by second answer times 18 divided by 5. I get a different answer. Did I make a mistake with this one? Let's check again. -2/5 raised to the 1/3 power times 9/25. Oops. Times that 4. That is the same? Wait, this one is negative and that one's positive. Oh my goodness. I feel like I have to try it again. Or, so you can try it again, or let's look at this other way of checking. Graph it. Graph this and ask, when is this equal to 0? When does it have any x-intercepts? So I'm going to type this in. We've got 4x squared, parentheses, x minus 1, close parentheses, raised to the 1/3 power, plus 6x, parentheses, x minus 1, raised to the 4/3 power. Okay. And zoom 6. Look, squiggle squiggle. So let's change our viewing window, because we know we have answers at 0 and 1, and this would be in between them. Let's change our viewing window to be -1 to 2. Okay. Here's our solution at 0. And then there's another one before we get to 1, and another one at 1. So yes, all three of these are solutions. So, all right. Excellent. So now we know we can solve equations with rational exponents. Okay. And I promised you in this video, must check number 3. Must check number 2 was squaring both sides. Must check number 3 comes up when we're solving absolute value equations. And instead of writing absolute value from now on, I'm going to write ABS, that's the button on your calculator, or math number at ABS, yes. So I'm going to write absolute value for when I talk about absolute value equations. So let's start off. 3x plus 2 equals 7. Now, with absolute value, I know that and that. So I know that with this one answer of 2, there could be these two different situations, a positive reality and a negative reality. So when I look at this equation, I want to say, well, I've got a positive component and a negative component. The positive component is 3x plus 2 equals 7. The negative component, we could write -3x minus 2. But, here's the thing. I know that -2 equals 2 and 2 equals 2. I know it makes sense to change those signs for my negative component. But it makes for more work algebraically. And I have to change the sign on two things. So what I'm going to recommend is you change the signs on one side of the equation. Instead of changing both of these signs, I'm just going to change this sign and write 3x plus 2 equals negative 7. Okay, so I have a positive component, I have a negative component. I got rid of the absolute value bars, I got rid of the absolute value bars and changed the sign. Okay, so now let's solve each of these equations. 3x equals 5, x equals 5 thirds. And over here, 3x equals negative 9, x equals negative 3. All right, so is this good? Well, let's see. Negative 3 times 3 is negative 9. Negative 9 plus 2 is negative 7. The absolute value of negative 7 is 7. That worked great. How about 5 thirds? 5 thirds times 3 is 5, because the 3's cancel. Right? 5 thirds times 3, 3's cancel. I get 5. 5 plus 2 is 7. The absolute value of 7 is 7. So that one works too. Mr. Cooper, that's not a must check. That worked out fine. What's the big deal? Well, what if we have this problem? What if we have absolute value of x minus 10 equals x squared minus 10? Okay, so same, right? I make the positive component and I make the negative component by changing the signs. Oops, I'm writing the positive component first, sorry. X minus 10 equals x squared minus 10. That's the positive component. And the negative component, negative x squared plus 10. Okay, so because this is a squared, let's move everything to one side. Minus x, and I add 10 and I add 10, and that's going to be no 10s. Okay, so then I solve this with factoring x minus 1. I get x equal to 0 and x equal to 1. Okay, and then over here with the negative component, I'm going to actually move these over here, so I have a positive x squared plus x minus 20 equals 0. Really? Why does that feel like a mistake to me? I changed the sign, I subtracted 10. X squared plus x minus 20. Yeah, that's good. So this is going to factor as x plus 5, x minus 4, and I'm going to get x equals negative 5, and x equals positive 4. Well, I think there's something wrong here. And I'm not quite sure what the wrong thing is. It's just that a little, my spidey senses are tingling. But let's check. Hey, let's think about this first, though. Before we pick up the graphing calculator, let's think how many solutions we expect. This is the absolute value v shifted right 10 places. This is a parabola shifted down 10 places. Do you see 4 points of intersection? I don't see 4 points of intersection. So I'm a little concerned about that. Okay, let's confirm with our graphing calculator. So we've got absolute value. By the way, absolute value, you have to press the math button, and then it's under here in number, ABS. Again, that was press the math button, go over to number, and there's absolute value of x minus 10. And I wanted it here, math, number, x minus 10. And then what was the other equation? This parabola shifted down 10. X squared minus 10. Okay, zoom standard. Yeah, I see only 2 points of intersection. So, not 4. Huh. Let's try. Let's see. Plug in a 0. 0 minus 10 is negative 10. The absolute value of negative 10 is 10. 0, negative 10. This is 10 equals negative 10? No, it doesn't. Let's plug in 1. 1 minus 10 is negative 9. The absolute value of negative 9 is 9. 1 minus 10 is negative 9. These aren't equal. How about negative 5? Negative 5 minus 10 is negative 15. The absolute value of negative 15 is 15. Negative 5 squared, negative 5 times negative 5 is 25. 25 minus 10 is 15. That works. And what if we try 4? 4 minus 10 is negative 6. The absolute value of negative 6 is 6. 4 squared is 16. 16 minus 10 is 6. Nice. So we got two solutions. But had we just done the work, we would have claimed all 4. This is a must check. This is our third must check. What is our third must check? Absolute value equals X stuff. When we have absolute value equals a number, that's not a must check. That's just an ought check. I ought to check that on a test. You know, if I have absolute value of x minus 1 equals 4, this is not a must check. Think about it. You've got this absolute value graph shifted over 1, and you've got this line y equals 4. There are going to be two solutions. Well, let's take a look. X minus 1 equals 4, the positive component. X minus 1 equals negative 4, the negative component. X equals 5, X equals negative 3. Two solutions, no problem. So when absolute value equals a number, that's not a must check. But if absolute value equals some X stuff, like X minus 10 equals X squared minus 10x. Now this is similar to, but different from the last problem we did. This was the last problem. Now I'm introducing this. Will you please solve this absolute value equation? Give it a try, pause the video, come back when you're done. Okay, welcome back. So my positive component is going to be x minus 10 equals x squared minus 10x. That's the positive component where I just take off the absolute value bars. My negative component is going to be x minus 10, but I have to change the signs. So negative x squared plus 10x. All right, what happens when we solve these equations? Well, I see a quadratic, so I have to move everything onto one side. I get 0 equals x squared minus 11x plus 10, or 0 equals x minus 10, x minus 1. I get x equals 1 and 10. Here, I'm going to move everything over there so I can have a positive x squared minus 9x minus 10 equals 0. And when I factor, I get this. Minus 10x, 1x minus 10x is negative 9x. I got the negative. Yep, that's right. And so I get x equals 10 and negative 1. So I have three different answers, 1, negative 1, and positive 10. All right. So does our absolute value equal some x stuff? Sure does. So this is a must check. So let's must check. Let's plug in 1. 1 minus 10 is negative 9. Absolute value of negative 9 is 9. And on the other side, 1 squared is 1, 10 times 1 is 10, 1 minus 10 is negative 9. That definitely does not work. What if I plug in 10? 10 minus 10 is 0. 10 squared is 100. 10 times 10 is 100. 100 minus 100 is 0. 0 equals 0. That works. What about negative 1? Negative 1 minus 10 is negative 11. The absolute value of negative 11 is positive 11. Here, negative 1 times negative 1 is positive 1. Negative 1 times negative 10 is positive 10. And so we end up with 11 on that side as well. So both of these work. Okay, so my answers are x equals negative 1 and 10 here. Great. Now, let's think about this graphically for a minute. You know, this is an up-pointing parabola with x-intercepts at 0 and 10. And this is the absolute value of x graph shifted right 10. So, how many points of intersection? One here at 10, and this other one here in negative land. And we found that that was negative 1. A positive 1, do the two curves intersect? Nope. So whenever absolute value equals x stuff, that's when you have a must-check situation. Okay. So I feel like I should do rationals. We did rationals. I want to do more rationals. Okay, so instead of making one really long video where I go through all of these, I'm going to stop here for assignment 21, and I'll pick up and do more of these in the next video for assignment 22. Because 21 and 22, it's pretty much the same assignment. You're doing the same kind of solving. So can't wait to see you in the